Hello, welcome to Sophie Co-Visionaries, me, Sophie Shepard-Natze. Our universe is full of unsolved and powerful mysteries, and one of the darkest being black holes. Do recent advancements in science shed at least some light on them? Well, to talk about this, I'm joined by 2020 Nobel Prize winner in physics, Sir Roger Penrose. 2020 Nobel Prize winner in physics. So great to have you with us today, Sir Roger. Yeah. Right, so when reacting to your Nobel Prize win, you said that the black holes have become an increased importance in our understanding of the universe. So let me ask you, as a layperson, why is the study of black holes so important?
Well, there's more than one reason. They're important partly because they're such strange things. We're used to space continuing more or less as it's like, and to find these strange objects which seem to be so different, where if you got too close, you might fall in and never be able to escape. And it's a very strange phenomenon. They are important for other entropy. I have to explain what entropy means. It's more or less randomness. And there is a thing called the second law of thermodynamics, which tells you that things get more and more random as time goes on. We have to keep the entropy down. This is how we exist. That's where we get structure. Structure forms and structure can be propagated, and we want to keep the entropy down all the time. Now, in black holes, this is where it all ends up. And why we have a universe which is interesting and complicated is really partly because of the black holes, because this is where ultimately the entropy goes down in the black holes, and we can then live off the residue, which is the low entropy of the rest of the universe. This is a simplified picture, but in a sense, although it's indirect, the black holes are absolutely central to our existence.
At the center of a black hole lies what's called the singularity, right? Where
Yes.
Density and mass become infinite. And the theory of relativity, which explains how gravity governs our universe, breaks down in the center of a black hole. And the gravity conditions there are too extreme for the theory of relativity to work, as far as I understand.
Yes,
so what kind of a theory about the universe will hold its own at the heart of a black hole?
Well, we don't know. What you would seem to need is a theory of quantum gravity. Now, you see, there's an interesting story here, because when I proved my theorem, and then that was to do with black holes, and this is to do with the singularities in the future. You could fall into the singularity, and it's the end. The opposite side of this picture is the beginning. We have, in the Big Bang, we have another singularity. And when I did my work, Stephen Hawking picked up on it and developed it mainly for cosmology. And he was more interested in the singularity in the past. And I remember I was in Princeton in the United States, and we were going to a conference, and we had to go in separate cars from Princeton. And I noticed in one of the cars, in the back seat, was Jim Peebles. And Jim Peebles was going up, and I thought, I'll take my chance. I would ask Jim, why don't cosmologists think of all these complicated kinds of singularities that you get in the future? We know many solutions of the Einstein equations, and they're very complicated. And you cosmologists don't seem to talk about them. And he looked at me and he said, because the universe is not like that. And I thought, my gosh, it's not, is it? Because the microwave background is all very, very regular, all over the sky. It tells us the Big Bang was very, very smooth and regular, and not like the singularities in the future. They're very different. So if we are to have a theory of quantum gravity, which explains the singularities, it's a very, very, very strange theory, which has to be different in the future from in the past. And that's not like the quantum mechanics we know. All the theories of physics, apart from the statistical theory, the statistical phenomenon of the second law of thermodynamics, everything seems to be symmetrical in time, backwards or forwards. What's the difference? So I thought, this is very odd. There must be some very strange theory which explains the difference. for many, many years, I tried to think of a strange theory of quantum mechanics, and I didn't get anywhere. But my student, Paul Todd, had a different way of thinking. Paul's idea is that you could extend the universe to before the Big Bang. That is to say, our Big Bang is the continuation of the remote future of what I call a previous eon. Now, the word eon, I like to spell it A-E-O-N, that's one of the spellings. It's a word which I looked it up in the dictionary to make sure it was not a million years or some length of time. It's an indefinite length of time. So I'm calling it an infinite length of time. So our eon began with the Big Bang and will continue to this remote future. There was an eon, I say, prior to ours. Its remote future became our Big Bang. And signals can get through. And two types of signals which we have existed on, and we looked for signals, gravitational wave signals from collisions between supermassive black holes, the waves coming out from the previous eon, we could see them, and we believe we do see them. And a Polish group also looked, and they also conclude that they see them. Nobody pays any attention because this is not the usual cosmology.
You've written a book where you're quite skeptical about the current application of quantum mechanics in physics, which seems to be quite in vogue right now. And you say that in the real world, quantum mechanics doesn't make much sense, hence Schrödinger's cat being a paradox. But even it's hard to grasp with, paradoxical nature of it with non-locality, superposition, and other mind-blowing aspects. Does that mean it's necessarily wrong?
I think you're new physics of the universe. Yes, I do express skepticism. But let me talk about the faith, that is the quantum mechanics. And what I'm trying to say, as you mentioned, the Schrödinger cat, and Schrödinger himself was trying to say that there is a problem with quantum mechanics. People tend to interpret it a little differently from Schrödinger himself. Schrödinger was saying, okay, according to his own equation, he was saying, well, according to my equation, imagine Schrödinger talking, you could have a cat which was dead and alive at the same time. And he's really saying, using this example, this is ridiculous. And that you couldn't have a dead and alive cat at the same time. The consequence of his own equation is that you have a cat which is dead and alive at the same time. Quantum mechanics is inconsistent with itself. You see, sometimes people say quantum mechanics is the best theory of physics we have ever had. I understand why they say that, but a theory is inconsistent with itself. And I don't think a theory that good should be self-inconsistent. Now, you see, since quantum mechanics works so well, people don't like to use the word inconsistent. They like to say, oh, it's amazing, or it's incomprehensible, or it's mysterious, see. But I say, it can't be quite right. And this is what Dirac says, this is what Einstein and what Schrödinger says. It's not quite right.
Okay, so I get your point, because it's provable and unprovable, and you're saying the same thing about the string theory, which is also quite popular nowadays. And it offers a very fantastical parallel universe Latin worldview. But for you, it doesn't hold up because of lack of hard experimental evidence. So is it just our current limitations in our experiments, or is the string theory completely improvable?
Well, you see, I think there's a big difference between string theory and quantum mechanics. String theory has no evidence to support it. Quantum mechanics has an enormous amount of evidence to support it. So there is no comparison. See, I don't like string theory very much. You see, when I first heard about string theory, I did like it. It was explained to me by Leonard Susskind, and I thought it was a very beautiful idea. And I was quite taken by it. But when I learned it had to have a space-time that was 26 dimensions, I said, okay, no. When they got it down to 10 dimensions, still, no, that's wrong. It says 4 dimensions, 1 time, 3 space. And if you tie up the other ones into a little ball and you can't, it's too small to see, that doesn't help. Doesn't work very well. I don't think it works. So I formed the idea quite early that theory is not correct. Whereas quantum theory is correct. But at one end of the scale, it is very, very close to being correct. So you have to say, what is it that makes it not quite correct? Well, that is where gravity comes in. So what I say is the union between general relativity and quantum mechanics is not that you bring the machinery of quantum mechanics to bring it into the fold of quantum mechanics. No, it's an even-handed marriage. There has to be give on one side and on the other side. Sure, Einstein's theory, when you look at tiny little spaces, 10 to the minus 33 centimeters, okay, maybe you chapter quantum gravity plays a role there. Maybe in the singularities, yes, you've got this sort of problem, it comes in. But that the main place where quantum mechanics and gravity have an effect on each other is the effect of gravity on quantum mechanics. It's the other way around. So I think, sure, we need to study how they interplay with each other, but don't have the view that quantum mechanics must be left intact. You must say, take the view that quantum mechanics must yield in the circumstances of the collapse of the wave function to gravity.
We're going to take a short break right now. When we're back, we'll continue talking to 2020 Nobel Prize winner in physics, Sir Roger Penrose. You have a rather daring theory of your own about human consciousness, which is rooted in quantum mechanics. And one of your points is that human thinking is not a series of executed algorithms, which means that any attempts to actually create a truly functional artificial intelligence using current computing powers are doomed. So in your view...
You have it right. Yes, you have it right. I mean, I don't know what artificial intelligence will do. And, you know, they can play chess very well. They play Go very well. I have some ideas about that, but never mind. But it's sure, it can do computations. We know that. I mean, it can do arithmetic much better. I mean, my father's Brunsviga machine where you turned a handle and it did arithmetic, that can do arithmetic much better than I can. But that's not the point. You see, this dates back to when I was a graduate student in Cambridge. Graduate student, yes. No, undergraduate, I think. Mainly when I was an undergraduate, yes. You see, I was doing pure mathematics. I was doing algebraic geometry. When I was a graduate student, I got interested in physics and on general relativity. That was not my subject, but yeah, interesting. Very good lectures, wonderful expositions he made. Another course on quantum mechanics by Paul Dirac. Beautiful, completely different style, beautiful, and I got my understanding of quantum mechanics from Dirac. The third course was a course by a man called Steen on mathematical logic. And I had been very puzzled by Gödel's theorem. You see, I thought Gödel's theorem seems to prove that there are things in mathematics that you cannot prove. I thought, this is not very pleasant. I don't like the idea. I went to the course of Steen. I learned about Turing machines. I learned about computability. I knew what that meant. I then learned about Gödel's theorem. He described the theorem. He says, if you have a system of logic, and provided you believe that the methods of proof within that system always give you truths. So that's say you follow the rules, and if the rules tell you true, do you believe it's true? You believe it's true if you believe the axioms are genuine, if you believe the rules of procedure only give you truths from old truths. Okay, so if it proves it's true, I believe it. Now, if you have that point of view, what does Gödel do? He shows a statement which says, in a certain sense, I am not provable. Now, you see, go through the procedures and you see, yes, if you trust the rules, this statement is true. Yet you cannot prove it by those rules. Now, those rules you could put on a machine. I knew about Turing machines. These algorithmic systems, sure, they are the same as computers. That means that this computational system, if you believe that what it says is true, if you believe all those statements, then you must believe the thing beyond its scope is true. Now, how does it do that? It does that by understanding. It understands what the rules mean. I mean, it doesn't, because it doesn't have understanding. That's what I regard as the difference. What does your consciousness do that is not done by the algorithmic system? It understands what it's doing. Now, what is understanding? I don't know what understanding is, but whatever it is something which is not following an algorithm. So it's not a computational procedure. Then I started to think, well, what can it be? How does it, it's something in the world. I mean, is it some mystical bougie whoosh that comes in from here, who knows where, that gives us some mysterious soul that enables us to understand things that a computational device cannot do? I didn't believe that. I thought, okay, what's going in our brains is material. It's just like the material in my computer. It's like the material in this lamp. It's like everything else. It's organized differently, perhaps, but it's still the same physical stuff. Okay, how do we see non-computable things in the world? Of course, now we know we can compute, not us, but some people, good people, can compute what black holes going around each other, swallowing each other, the signals they produce in gravitational waves. If you build LIGO detector, another Nobel Prize, you can see these signals which follow what the calculations tell you that black holes spiraling into each other do. Sure, you can do general relativity on a computer. What about quantum mechanics? Yeah, you can put Schrödinger's equation on a computer. Then I go to the position principle. He said, okay, an electron can be here, or an electron can be here, or it can have a state where it's here and here at the same time. He takes out his piece of chalk. He breaks it in two. I think he breaks it in two. He says the piece of chalk, first within one, chalk can be here or two, or can it be clicked into here and here in the same time? My mind wanders. I look out of the window. I'm thinking about something else. Then he finished his explanation. He comes back. I have a vague memory. He's saying something about energy. I have no idea what he said. He goes on. He talks about quantum mechanics. So I'm left with this puzzle. What on earth is it that makes the piece of chalk behave differently from an electron? He must have explained it to me, but I didn't understand. So I go on thinking that must be where the problem lies. Something about big, they can't somehow exist in two places at once. The wave function collapses under the weight of gravity in some sense. So that was kind of a vague thought, but I nevertheless thought that. And if consciousness depends on that thing, there has to be in the brain somewhere where the collapse of the wave function, whatever that physics is harnessed by the brain. Now, it's the opposite of what many people used to think. Many people, such as Wigner and I believe von Neumann, used to believe that, at least possible, that it's conscious being observing the system that collapses the wave function. So it's our consciousness which collapses what we look at, you see. My view is the opposite. It's not that. It's what makes the consciousness is the collapse. So it's the other way around. I have no book. Now, it took me a long time actually to galvanize myself to write the book. This was The Emperor's New Mind. Eventually, I did decide to write the book, partly because I heard some of I think it was Marvin Minsky and Edward Fredkin talking about what computers could do in the future. And you have these two computers talking to each other. And as you walk up and to the computer, they've already communicated more ideas with each other than the entire human race. And I thought, well, I know where you're coming from, but I don't have that view. I think understanding is something else, not the computer. And so I thought, well, I will try to explain my point of view. And then I realized I have to learn about neurophysiology. So I have a section where I learn about neurophysiology. I learn about the Hodgkin-Huxley theory of nerve propagation. And I think, can I get enough coherence? You have to have a quantum system to preserve itself up to a sufficient level that it actually does something in the brain. Nerves, well, the nerve signal propagates its electric field all over the brain. So it's no hope, no hope, no hope. I got to the end of the book. I had to finish it. I did something I didn't really believe in, and that was the end of the book. Rather disappointment at the end. Nevertheless, a few people read my book, including Stuart Hameroff. Now, Stuart Hameroff is an anesthesiologist. That's the way they call it in the United States.
We actually did an interview with him, so I know exactly what you're talking about.
Oh, did you? Interesting. Yes. No, he told me about microtubules. You see, I hadn't never heard of them. You see, so he said, "Okay, these little tubes. This is probably the solution to your problem." So I thought, "Gosh, is this another crackpot? I get crazy letters from people." And I thought, "Well, I look it up. Isn't microtubule real?" Yeah, it's real. So I thought, this is very interesting. So I got to talk to him. He came to England, and we had long discussions, and then we had many other discussions. Not only are they more promising than because they're small structures, but they're very symmetrical structures. So I was very impressed by the symmetry that you get in these little microtubules. And I thought there was a much better chance. So we then got together and we formulated our orchestrated objective reduction theory, which Stuart, I mean, he does the biology and the neurophysics and all that stuff. I don't understand that stuff. And I do the physics. He doesn't understand the physics very well. So we get together and complement each other in this way.
Well, Professor, I mean, Sir Roger, it's been this brilliant lecture on your behalf on all existing theories and which of them stand ground and which not. And I thought, this is much more interesting than me asking you silly questions. So thank you so much for this wonderful insight into, you opened a curtain into how our world functions beyond this dimension. So thank you very much. And if possible, maybe we can do this one more time.
My pleasure. No, I've enjoyed it. And
thank you so much, Sir Roger.
Thank you. My pleasure.
Thank you. Take care of yourself. Thank you.
Thank you.